Yeah, false. Some people got true. This is just memorization. I just checked it against your notes. Number 3. E. Number 4. True. Physical property would be like mass. That would differ. Number 5.
C.
C is electron. Everybody got C?
D.
D? D is correct. So some people this morning argued the electron. It should be an electron. That's the smallest piece. But you know, would an electron be the smallest piece of copper? No. So copper is an element. So that's. But I can see their point because they're arguing, well, copper is made up of electrons. But you know, I'm asking for the smallest piece of copper. I'm sorry?
Would an atom be the correct answer?
Yeah, that would be the correct answer. It says would an atom be the correct answer? Yeah. That's atomic theory. 6. You got it. True. 7.
C. Electrical.
Yeah, C is correct. 8. B. 9. False. This is 1,000 milliliters. 10.
False.
False. Right. 11. False. 12.
False.
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 False. 13. 2 sig figs?
3 sig figs.
3 sig figs. 3 sig figs. You have 3 here, 4 here, you're going to get 3 sig figs. 14. 4. 15. Helium. Helium's heavier. Which one's bigger? Hydrogen's bigger. We can understand that based on the structure. So I talked about that this morning. Let me just talk about this briefly. Well, why wouldn't helium be bigger in size? It's got more stuff. And the reason is because of electrical attractions. If we look at hydrogen, hydrogen has 1 proton for the H1 isotope. For the H1, we have 1 proton and what else? 1 neutron. For H1, there are no neutrons. It's just 1 proton and 1 electron. You know what holds the proton and electron together? Is it gravity? Do you know what holds the Earth and Moon together? It's gravity, right? But what holds the electron and the nucleus together? Is it gravity? No, it's not gravity. Gravitational forces are pretty weak unless the mass is huge, like the Moon and the Earth. If the mass is small, then we pretty much ignore gravity. Yes, there is gravitational attraction between 2 masses, but the gravitational attraction here is negligible. What's important is the electrical attraction. And so this is a hydrogen. And then if we look at helium, helium doesn't have 1 proton. Helium, we'll look at this isotope. This is the most common isotope of helium. This helium isotope has 2 protons. How many neutrons? 2 neutrons in the nucleus. And so when we look at the total charge here, the total charge is +2. The total charge here is +1. And so if we have an electron, actually helium doesn't have 1 electron, it has 2 electrons. The 2 electrons try to stay away from each other. They try to stay away from each other because they're the same charge. charge. So, but the electrons stay away from each other, but the electrons are attracted to the nucleus. And so Coulomb's law says this. Coulomb's law says the force of attraction or repulsion is proportional to the charge on the nucleus times the charge on the electron divided by the distance between them. Actually, the distance between the center charges, squared. And so over here, if we look at this, this is -1 for the electron, +1 for the nucleus. And so it's going to be minus and +1. And so on the numerator here, we'll get 1. Over here, we'll have +2 times -1. We'll get -2. So a -2 versus a -1, what this tells me is that the force is twice as strong, given the same distance. And so if the force is twice as strong, this is like in the sci-fi movies. In the sci-fi movies, they have like the tractor beam that pulls in objects. Well, this is like the tractor beam here. The tractor beam over here is twice as strong as over here. And so what that's going to do is it's going to pull in the electrons close to the nucleus. Much stronger electrical attraction. If it pulls in the electrons much closer to the nucleus, then we say it's a smaller atom in size. It's going to weigh a lot more. It's a lot heavier. It'll be more dense. All right, 16. How many sig figs are 9/5? Infinite. 17.
False.
False. 18. True. 19. False. 20. Well, we have to qualify 19. 19 would have been true many decades ago, but not anymore. 20. True. False. What is a substance? Substance is pure. Usually, it's a pure substance. It would be, for example, is sugar, water a substance? No, because we would classify things as either substances or mixtures. So sugar, water should be a mixture. So what types of things constitute substances? Is water a substance? Is gold a substance? Is sugar a substance? Yeah. You have pure table sugar. Sucrose is what sugar is. Table sugar is sucrose. So if we had sucrose, yeah, substance. And so tell me the definition of a substance. Does water have fixed composition and fixed properties? No. Yes. Is water a substance?
Yes.
Do substances have fixed properties and fixed composition?
Yes.
So it's true. How many sig figs are allowed in the answer? Here. 2? Is that what everybody got? Actually, you should go through this test. Thing is, I don't like to post the key to this, and I don't really even like to go through it question by question, because I want you to work to find the answer. You can work to find the answer by looking it up online or trying to find it in our textbook, or at least try to track down the answer and then answer it yourself in that way. You do this before so that you have time to absorb it and then remember it, but B is wrong.
Should be 1.
It should be 1. There's 1 sig fig allowed in the answer. That's because it's subtraction. When we do subtraction, we always set it up aligning the decimal places. 1.22 minus 1.1, and then I'll add an extra 0. This extra 0 I'm just tacking on just as a placeholder. 2 minus 0 is 2. 2 minus 1 is 1. 1 minus 1 is 0. So we get 0.12. This number is an extra digit, so we got to round that off. This could be 0.1, which is how many sig figs? 1 sig. 22. Compounds can be separated into elements using techniques such as electrolysis. This is true. Last semester, I demoed electrolysis when I was talking about chapter 1. This semester, I didn't. The reason I didn't is because our power supply is so weak. This has been on for hours now. And what I have in here is water. And so in electrolysis, we're just passing a voltage, electricity through water. If we pass electricity through water, what happens is the water decomposes. Over here, I have some hydrogen gas forming. Do you see the pocket of gas in here? That's hydrogen gas. Over here, I know this is oxygen gas. How can I tell? Take a look at the ratio. Do you see the ratio? It's 2-to-1 ratio. I'm forming twice as much hydrogen gas as oxygen gas here. And so this is going off. You can barely see it, but it's bubbling here. You could do this with a 9-volt battery. But we're doing this with this power supply here. So this is called electrolysis. We can separate the hydrogen from the oxygen in water using electrolysis. And so I showed this last semester, but you gotta remember each semester is a little different. So your test might not exactly match their test because I might have emphasized something else, you know. And since I emphasize different things in different semesters, that's why you need to make sure you have that down in your notes. Because something else might pop up, you know, kind of like this, which I didn't talk about last semester, but I talked about this semester. Those kind of things happen. All right, 23. 24. 23 is false. 24 is B. Anybody else get B?
Yes.
You got B? Anybody else? Yeah. Yeah, you're going to get a periodic table. So let's take a look at the periodic table. What are the numbers in the periodic table?
The atomic mass, average atomic mass, and
Yeah, how about this number here?
the mass number.
Atomic mass. Is that the atomic mass or is that the
That's the
atomic number? Because actually we have various numbers here. We have the what we call the mass number, and then we have the atomic number, and then we have the atomic mass. So the number 15 is the atomic number. This number here is the atomic mass, which is AKA average atomic mass of all the. But you know, phosphorus only has how many isotopes? One isotope. Therefore, all the phosphorus atoms weigh this, and this is about how many U? Just roughly, how many U? 30 or 31? 31 U. So if a phosphorus weighs 31 U, then and the mass number is the protons and neutrons, then it's got to have around 31 protons and neutrons altogether. And so this is going to be close. I'd say the mass number should be 31, right? The mass is 30.973762. Otherwise, if the mass number were 30, then where's that extra 1U coming from? The electrons? No. Electrons don't weigh much. And so the correct answer is C. 15 plus 16 is 31. It can't be B because that would only give you 30. And if you have 30 protons and neutrons, that would be about 30 U. And so we have one extra U. But we don't have enough electrons because electrons weigh 2,000 times less. And so to make 1 U using electrons, you'd need 2,000 electrons to make 1 U electrons. 25.
False. C.
False. Oh, that reminds me. Sometimes I do this, unfortunately. Like, if you look at this, yeah, we said how many? And so what do you put on the Scantron? C, yeah. So I would have corrected this on the board. This should have been A, B, C, not A, B, B. That's a typo. $25. B, okay. 26. A is correct. 27. Do any of these answers make sense? No. And so this is a mistake on my part. What is the correct answer? Is it 0.0123 or is it 123? And you could tell really quick, 0.0123 or you're moving the decimal 2 over. So I can move it to the left or I can move it to the right. You know, the quick way of determining this is this. Take a look at the exponent. If the exponent is going from 10 to the minus 10 to 10 to the minus 12, minus 10 versus minus 12, we're making it smaller or bigger? Smaller. So if this grows smaller, then the coefficient has to grow bigger. And so it's not 0.0, it's got to be 123. 123. And so the correct answer is 123. 123 times 10 minus 12. This problem, the reason I use these particular numbers is because they have some meaning to them. You know, what's the meaning to this? You see something there? Mm-hmm.
Just 10 to the negative 12 is picometer.
Yeah, picometers. That's good. Picometer. You know what 10 to the minus 10 meters is defined as? Angstrom. Good. And so this, you know, this is something you catch if you know this. You know, 1.23 times 10 to the minus 10 meters is equal to 123 times 10 to the minus 12 meters. And so basically it's this, 1.23 angstroms is equal to 123 picometers, which is about the diameter of an atom. The diameters of atoms are going to be either in terms of angstroms or picometers. But people have an aversion to decimal points, so people like having no decimal point there and then using that. But when you see numbers like this, you know, 1.23 times 10 to the minus 10, then we're talking about the order of an atom size of the atom. Or 10 to the minus 12, of course. Hundreds, picometers, or single digits. 28. Again, the answers don't make any sense here, so I've written something on the board. A would be true, B would be false. So Dalton came up with the first significant atomic theory. True. 29. J.G. Thomson's CRT experiments. False. 30. Temperature is a measure of motion. Sure. $31. The three main types of motion. True. 32.
False.
False. 33.
True.
False. It's a trick question. It's false. Looks like the temperature doubled, but it really didn't double. Temperature is really based on the absolute scale. So the correct answer is false. 34, however, the temperature did double. If the temperature doubles, then the pressure doubles. 35. I accepted C or B. I did not accept A, and I did not accept D. So B or C would have given me credit for this one. C if we tighten the range of temperatures. 36. A is correct. 37.
True.
It's false. Translational motion means what? You go from point x1 in space to point x2 anywhere in space. That's translation. Free to translate anywhere you want. So if you look at the water molecules in ice, are they free to move about wherever they want? No, they're locked in position. If they're locked in position, then that means they have no translational motion. And so solids have no translational motion, true. There are some exceptions in which some of the atoms in a solid might have translational motion. But those are rare. And most of the atoms won't have translational motion. Otherwise, if there was translational motion, it would be a liquid. It could flow, or it'd be a gas. 38. Gas pressures are, yeah, true. 39. C is correct. You know, the equation, the zeros are different. PSI A and PSI G, the zeros are different by 414.7 if it's normal barometric pressure. So it's like Kelvin, you know. So the Kelvin and Celsius are different by how many? 273. So if you have Celsius, you have to add 273. Well, if you have PSIG, you have to add 14.7 to get the absolute. So the exact same as algebra. We would be able to do this dimensional analysis if we had the zeros match. But since the zeros don't match, we have to use an algebraic equation, that is, we have to do some addition. Just like Fahrenheit and Celsius, it would be on the plus 32 and minus 32. 40. That's true. 41? True. That's true. $42. Is true. 42 is not true. 42 is false. Why is it false?
It's made out of compounds.
It's not. Water is made up of compounds too. Water is made up of the compound containing hydrogen and oxygen, H2O. Carbon monoxide is made up of molecules. How you know this is not true is this is like the bit of memorization. You know, how do you know water is a liquid? Because you learn water is a liquid. How do you know sodium chloride doesn't form molecules? Because you remember or memorized it doesn't form molecules. Instead, it forms something else. Does anybody remember what it forms? What it's called? Yeah, a lattice. I gave you two types of lattices. Ionic lattice and, yeah, so sodium chloride is an example of an ionic lattice. It's going to look something like this. That's not a great picture of the lattice, but it's crystals. This would be a sodium chloride crystal. But when you look at the arrangement of the atoms, it looks like this. Do you see any, molecules should be a discrete unit. Do you see any molecules in there? Like a discrete unit? The blues are the sodium, the greens are the chlorines. Do you see a molecule of sodium chloride in there? No. This is what we mean by lattice. What was the other example of lattice I gave you? At the same time. I told you not to worry about ionic at that time because ionic we'll talk about later, but it's a lattice. And the other type of lattice was the covalent lattice. Oh, good. Good. And the covalent, we'll talk about what covalent means, but what was the example of a covalent lattice? Quartz, exactly, quartz crystal. Quartz crystal, are there molecules of SiO2? And so if we look at quartz, let's look at the quartz crystal. But I don't want just a crystal, I want the structure, quartz crystal structure. Obviously the quartz crystals are really pretty, but when you look at this, do you see a discrete molecule of SiO2 in there? Maybe it's hard to see. I mean, it kind of looks like ice here. But when we do this and we look at the structure broken down, do you see a discrete molecule in this small molecules of SiO2? No. This is what we call a lattice, and this is not an ionic lattice like the salt. This is a in covalent lattices, they like to show these things, these linkages, which are called covalent bonds. But we'll talk about that later. This is the covalent lattice. This is the ionic lattice. Things that form lattices like this do not form molecules. Well, what else forms a lattice? One time I was watching the news and somebody was talking about, copper. And they're saying copper is made up of molecules, and you get it down to the very basics of molecules of copper. Is copper really made up of molecules? Sure. And so we might think, yeah, copper is made up of molecules, but when we look at it, this is the structure of copper here. Do you see the molecules of copper? Is this one cube a giant molecule of copper? No, because molecules have to be a discrete unit. This is what this giant cube is. This is a very tiny crystal of copper. But I don't see any molecules of copper. I just see copper atoms in a lattice. This is a metallic lattice, metal lattice. And so there's actually, I didn't talk about metal lattices. I just talked about ionic lattices, covalent lattices, and we have metallic lattices like this as well. So the correct answer is table salt is made up of molecules? No. It's made up of atoms arranged in a lattice. 43, what did you get for the temperature? Today, somebody said, well, they got 30,000 Kelvin was the temperature that they got. 30,000 Kelvin, what do you think about that? Absurd? 30,000 Kelvin. Do you say that's absurd or okay? The thing is, a lot of people might say, that's okay, 30,000, because that's the answer I got, is 30,000 Kelvin. But you need to memorize a little bit of data, a little bit of factual knowledge to know that, so to illustrate this 30,000 Kelvin, You know, let's see, let's have some reference points. What's the hottest object you probably know? Maybe the sun is the hottest.
Yeah.
And so, temperature of the sun. Let's take a look at the temperature of the sun. The surface temperature of the sun is 5,778 Kelvin. But the internal temperature of the sun can get up there, like 30,000 Kelvin. But it's not homogeneous, 30,000 Kelvin. It's heterogeneous. Electrons can easily get up there, but the other atoms might not. And so we need some reference points to make it sound reasonable, because you know somebody might ask you the size of the atom, and you do your calculation. Well, I just did my calculation. The size of the atom I got was 1 times 10 to the minus 20 meters. And you go, okay, but you know, people, pretty soon these numbers start meaning nothing, you know, because they're abstract. And so you have to make them not abstract. Like if you can make the connection between these are abstract, right? But if you can make a connection between these numbers and the size of the atom, then you have a much better idea of what these numbers mean. And so 30,000 Kelvin is a little bit too high. So there's a mistake. What is it? Well, it came out to about 3,000 Kelvin. It comes out to 29, what was the answer? 2980? 2,980 Kelvin. Is that okay or is that extreme? 2,980 Kelvin. And then we need some other reference points to memorize. So for example, do you know how hot the flame is? The temperature of a methane air flame is like 800 to 1,000 degrees C, maybe not quite 1,000, maybe 800 degrees C. You know, 800 degrees C is about 1,000 Kelvin, so the temperature of the flame is about 1,000 Kelvin. And so in this particular problem, we're good. You know, if this metal cylinder got thrown into a flame, then it should be able to withstand that temperature, right? Because this metal cylinder should be able to withstand 2,000 psi, and to get 2,000 psi would take 2,980 Kelvin. We're okay. But if you know some other numbers, you know, these are little things you can go. You go, okay, I just calculated that metal cylinder is good to 2,980 Kelvin. Did other people get that number? 2,000, you got it? Okay, 2,980 Kelvin. But other people might laugh at you. Why? And you go, I did the calculation right. Why are you laughing? They might laugh at you because what temperature does metal melt at? And so if we go, okay, the metal cylinder is probably made out of steel. And so if we search the melting point of steel, what is the melting point of steel? Roughly. It depends on what type of steel it is. Steel is a mixture. Steel being a mixture, does it have a fixed melting point? No, it depends on what type of steel you get. Stainless is going to have a much higher melting point than this, but this is mild steel. Mild steel has the lowest melting point. It's like iron, mostly. Some carbon steels are hard, but about 1,427 degrees Celsius. So that cylinder probably isn't going to melt in this flame. But will that cylinder last to almost 3,000 Kelvin? No, because that cylinder is going to melt well below that. And so if you know these little numbers, you might be able to know these little facts, and you're calculating these numbers, you can put a much better perspective on these types of things, you know, or at least be aware, because you might do this calculation and say that metal cylinder is safe. It won't explode, it won't blow up until temperatures of 2,980 degrees Celsius, but you're going to be in trouble well before then, especially if that's a dangerous gas, you know. If that cylinder melts, it's going to release all that gas. 2,000 psi of gas is very dangerous. When you start working with compressed gases, you have to go, this is an OSHA requirement, you have to go through gas safety training. And so if you have a 2,000 psi tank like that that's filled with, let's say, nitrogen, then it's easy to kill yourself. It's easy to kill yourself because that's a lot of pressure. What can happen is that can just purge all the air out of the room, and you just die from asphyxiation. People have died from that in the past. And so what we want to do is we want to just learn or memorize little facts here and there. Like, do you know what metal has the highest melting point on the periodic table? What would you guess? Just take a guess. What metal would you guess would have the highest melting point?
Tungsten.
Lead is a pretty low melting point. Tungsten has a very high melting point. Tungsten has a very high melting point because they use that in light bulbs. Those you got to get the metal hot to make it start glowing in the old incandescent light bulbs. And so if the metal melts, this is why who was it? Edison picked tungsten. Edison picked tungsten because of its extremely high melting point, hard to melt. Unfortunately, tungsten is prone to corrosion and oxidation. And so to protect the tungsten from corrosion and oxidation, do you know what he did? He surrounded the tungsten, not with air, but he surrounded the tungsten with an inert gas or semi-inert gas like nitrogen. Right. And so if you fill your light bulbs with nitrogen, you don't have to worry about oxidation occurring because the tungsten, when it oxidizes, it forms an oxide. And when we form an oxide, it becomes very brittle and breaks. So if you try to light your light bulb, I don't know if you've done this, try to light your light bulb with a cracked glass and then watch the tungsten oxidize and then collect the tungsten afterwards. Is very fragile, it's very brittle. It's not metallic, but tungsten is one of them. But what would you guess that's the highest? What would you guess is the highest? What had the highest density? Mercury has a very high density, but it's not the highest. Gold has a higher density, but gold's not the highest. What has the highest density? It's not that much higher than gold. Platinum, iridium, osmium, those have the highest density, and they also have the highest melting point. In fact, the melting point of platinum is 1600 degrees C. So if we made this cylinder out of platinum, then it could withstand a little higher temperature, 1600 degrees C instead. I used to use a platinum furnace. If you have an electric toaster oven at home, how hot can it get? Nowhere near that hot. And so if you really want high temperatures, you're either going to use a blast furnace or you're going to use a platinum electric furnace. A platinum electric furnace can get up to almost 1600 degrees C, or about 16 without melting. And so I had to cook things at very high temperatures, like 1300, 1400 degrees C, using a platinum furnace. That platinum furnace was very expensive at the time. I think it was like $50,000, but in today's dollars, it would be over $1 million, I think. I don't know what they did with it. When it gets old, do they throw it away? Should have kept track of it. All right, so the general knowledge is, the memorization stuff and memorizing little things here. Of course, you can't memorize everything, but these little things that you can memorize by repetition will help you understand the a lot better. So 43. How many Celsius is that? About 2600, 2700 Celsius. Okay, there. All right, number 44. Any problems with that? What did you guys get for the temperature? 44. How about number 45? What do you get for number 45? Nobody? All right, let's go to the homework. Let's see, look at the homework and see. There are questions on that. I'm not going to do this for every test, like go through a heavy review, because we don't have enough time. But for this test, we can just go back and review. What do you guys want to review? I'll just fall behind a little bit. We can catch up later. What do you guys want to review? Or what specific topics do you want me to cover? Uh-huh.
So, like that question on the board, you're kind of temperature and Kelvin. How many, would you say that the pressure each of them has one significant, or would you say that the
What I say, okay, this is ambiguous. I would either say one significant figure for the pressures or infinite. You know, if this were a thought experiment, you know, hypothetically, if I start off at 200 psi, what temperature will it get up to 2000 psi? Then I would just leave it exact and put the sig figs rounded to whatever other numbers I have. So I'd do that. And the other numbers I'd have is this. Well, this is, you know, you could call this exactly room temperature, quote unquote. But this one is not going to be exact. There's going to be a limit. So we'll just round to what seems appropriate. And what seems appropriate is, I already dropped off the decimals because this is actually 298.15, but let's do it to the nearest degree. See. Uh-huh.
Would you give me a specific question? Would you be number 33 in chapter 3?
Number 33, chapter 3. Do you know what section that was in?
Section 5.
All right, well, a woman stands on a scale in an elevator in a tall building. The elevator starts going up and rises rapidly. And so if the elevator, as you're going up, do you feel more pressure on your feet or less pressure? More pressure. And so actually, if you put a scale underneath your feet when the elevator goes up, will you weigh more, the less, or the same amount? If you put a scale under your feet, you're gonna weigh more because of the force. Not only do you have the force of gravity, you know, but you're accelerating upwards, and so you're gonna feel the what they say the G's. You know, you feel this in the car too. Under heavy acceleration, you get pushed forward or pushed back. You get pushed back. So if you put the scale on the back of the seat, you're going to measure the force, you know, the pressure, the weight. You know, if you brake suddenly, then you're going to go weightless, you know, because you aren't going to have as much pressure or force or weight on the back of the seat. And so compare the woman's standing weight as recorded by scale and her mass while the elevator is standing still and during the starting period, during the constant rate period, and during the slowing period. And so let's just look at the weight. The weight standing still, okay, nothing's happening. And then as it accelerates up, they're going to weigh more. And then if it's going up at a constant speed, then what? Weigh the same. And then if they slow down or decelerate, then what should happen? They'll be lighter. Does that sound right? Uh-huh.
So there's no like calculations or anything you have to do?
No calculations. This is just, this is just based on your observations. Then what we do is, if that's just based on your observations, her weight is the same when the elevator is standing still and when it moves at a constant rate. It decreases when the elevator slows, it increases when the elevator accelerates. It's just a feeling, This is all, you could get all of this in Newton's law. We could do calculations for this, but we aren't. It's just, based on your own personal observations. That's it. However, does your mass change? The mass is the measure of how many atoms. Did you lose any atoms going up or no? And so you still have the same number of atoms, and the atoms' masses don't change. All right, other questions? Okay, chapter 3 or?
Yeah, 97.
97. Now, for chapter 5, if I'm not going to collect the homework, I'm also not going to have all of chapter 5 on the test. If you look at the test from last semester, I only went up to what section of chapter 5? We'll take a look at it in a minute, but after we finish chapter 4. $97. It takes 7.39 kilocalories to melt 92 grams of ice. And so we can just write that down. That would be a conversion factor, ratio, or relationship. So the way I'd write it down is like this: 7.39 kilocalories. Kilocalories. This is abbreviated kcal. To melt 92 grams of ice. 92 grams of ice melted. Calculate the heat of fusion. Now, what the heck is heat of fusion? So we have to look that up. A hint, see question 95. So let's take a look at question 95. Maybe that'll tell us what that is. And so we go back to question number 95. The amount of heat, Q, absorbed when a pure substance melts is proportional to the mass of the sample. Express this proportionality in mathematical form. Change it into an equation using the symbol delta H of fusion for the proportionality constant. This constant is the heat of fusion of a pure substance. If heat is measured in calories, what are the units of the heat of fusion? Write a word definition. Did I assign this problem? No. So what is the heat of fusion? This is heat of fusion is the amount of energy required to melt. This is called the heat of fusion. Fusion is another word for melting. If we look at it, it's the heat this is the energy. It's the heat energy over the mass. And this heat of fusion is given the symbol delta H of fusion. So H. Well, anyway, this is the heat of fusion, which is the amount of energy per mass. Well, here we have the amount of energy, here we have the mass. The only difference is, in typical heat of fusion, we do it per 1 gram, not per 92 grams. If we do it per 1 gram, then we just take that number divided by 92. So it'd be 7.39 divided by 92, which gives me 0.0803. How many sig figs am I allowed? I'm allowed 2 sig figs. I'm just going to carry 1 extra. 0.0803. And the units here will be kilocalories per gram. Well, kilocalories is not the best unit. The best unit would be a calorie. So to convert from kilocalorie to calorie, calorie is smaller or bigger than a kilocalorie?
Smaller.
Calorie is smaller. So if I make the unit smaller, I need to make the number bigger, and I got to move it 3 decimal places. So this is going to be 80.3 calories per gram. Okay, so what I need is 80.3 calories of heat to melt 1 gram of ice. This is the heat of fusion. If heat is measured in calories, what are the units of the heat of fusion? Well, calories per gram. Change it into an equation. Well, this is the equation. Write a word definition. Word definition is the heat of fusion is how many calories it takes to melt a gram of whatever. Heat of fusion. Yeah. So how many calories? Let's see their answer here. Rearrange the equation there. I didn't. Heat energy lost or gained per gram while changing state from liquid to solid or vice versa. No. No, heat of fusion is solid to liquid. You know what fusion means? Fusion means melting. Melting means solid to liquid. If we go in the opposite direction, we don't call it melting. If we go from a liquid to solid, we call it not melting. What's the opposite of melting? Freezing. We call it freezing. The heat, or delta H, freezing. So it's a little different. Energy turns out to be the same, but we just have to remove it rather than give it. All right, so that was it. And so we're down here. Calculate the heat of fusion of water. So we just calculate the heat of fusion here. How could we're given the heat of fusion? This is the heat of fusion. Essentially, we just had to put it in this ratio, and then we just simplify it to make it rather than per 92 grams, per 1 gram, and we end up with this. Here, you know, if I didn't want to write this in scientific notation, is that 2 sig figs? Or is that 1 sig fig? 1. Is this 2 sig figs or 1 sig fig? This would be 2 sig figs. If there's a decimal place present, these zeros are significant. All zeros are significant, fall into non-zero, and if there's a decimal place present. Okay, other questions from chapter 3? Want to go through? All right, do you want to work straight through, or do you want to take a break right now? Take a break? Let's take a break then for 10 minutes or so, and then we'll start. Yeah. Take a look back through your notes or whatever else, and we can cover the sections that you want.